Alright, so you're not going to be around to do the simulation portion. Just so you know that when we go from one trial to 4 trials, the mean should stay the same. And sigma should cut in half. Actually, I should call this S because we're doing a sample. And when we go from 4 to 16, it gets cut in half again, approximately, because once again, when we do samples, things don't always work out exactly the way we want it to. So here are some facts about means and variables, and it should say variance, and we're actually going to have 3 of them. Okay, so X bar is an unbiased, or it should be, estimator of mu, and the standard error. Alright, and then the standard deviation gets smaller by a factor of the square root of n. And when you're taking a sample, same as the proportion, the population must be 10 times the sample. And in here it should be at least 10 times the sample, so that gives us independence. And of course, for all of this to be true as well, if we were doing this with the population, we will want an SRS. So the real life applications for this, the real life application is basically to see if whether things have stayed the same or if the mean has changed from what we thought it would be. And we'll do more real life applications in the next chapters. So the expected value for X bar is the same thing as mu, and assuming that we have independence, the standard deviation of X bar equals the standard deviation divided by the square root of n. So this is where the square root of n comes in. If you remember from yesterday, the square root of n was also in the denominator of the standard deviation of proportions. So let us try these problems in example number 1. So in example number 1, we have a normal distribution, mean is 64.5 and the standard deviation is 2.5. And what are the chances that you pick one woman at random that she is taller than 66 inches? So here's my normal distribution with the mean of 64.5 and the standard deviation of 2.5. We want to find out that someone is taller than 66 inches, so right here we'll make that black line 66 inches, and since we're shading above, we're going to go above. So X equals the woman's height. Probability that X is bigger than 66, so normal CDF, first line is 66 to a big number, with a mean of 64.5 and a standard deviation of 2.5. And we get 27.4%. And now we're going to try it again for B. So same situation, except instead we are going to pick 10 people. So my mean is still 64.5. My standard deviation, though, is 2.5 over the square root of 10, which means my standard deviation is all the way down to 0.791. And by the way, when we take the average of a bunch of normal distributions, it's still going to be normal. So now 66, since the standard deviation is so much smaller, 66 is farther away from the mean, it looks like. And we're going to do the same thing with the normal CDF, except for the standard deviation is now 0.791. So now we're down to the probability that X bar is bigger than 66. This is the mu of X bar. This is the standard deviation of X bar. This is X bar is 0.029, which means that if I was taking an average, it's a lot harder to get a number that's bigger than 66 out in the tail. So let's do the same thing with C and D and see how it works with something in the middle. So in this particular problem, we still have the mean of 64.5. The standard deviation is going to be 2.5. And then this time we're taking our values in between 63.5 and 65.5. So this one over here is 63.5, and this one over here is x equals 65.5. So we're looking for the probability that x is in between 65.5 and 63.5. So we're going to normal CDF again. So I'm just going to write down CDF from 63.5 to 65.5 with a mean of 64.5 and a standard deviation of 2.5. And that gives me an answer of 0.310. Now, for the last problem, we still have this 64.5, which is the mu of X bar. We have 63.5, which is the X bar over here. And we have 65.5, which is the number over there. And this time, sigma is once again 2.5 over the square root of 10. Which is still 0.79. So, what is the probability that X bar is in between 63.5 and 65.5? We once again use normal CDF. And we only had to change the standard deviation to be 0.791 again, and this time we get an answer of 0.794, which means that when we take averages, there's going to be more data that's close to the mean than it is when we just have the one person. And same thing with the edges. The edges get smaller when we have a bigger sample size than one. And this will come up often. Please email me any questions, and that's it for this lesson.